Okay, let's talk about shadow prices. We said in the last video that the values that are in the objective row beneath our slack variables are called dual variables, also called shadow prices. And so let's talk a little bit about that interpretation as shadow prices. And so we said that after we sort of change our basis or change our tableau, do our row operations, and really once we get to our final tableau, we can write our objective value as these dual variables times our right-hand side of our constraints. Okay, and so we're essentially saying our profit or whatever our objective value is some numbers multiplied by our right-hand sides. And so that gives us this interpretation of these y values, these dual variables as being shadow prices. And it comes into the idea that our right-hand sides of our matrix, at least in a maximization problem, are usually talking about limited resources. But in most cases, they're limited based off of managerial decisions, right? If we could show that there's a benefit, we could get more resources devoted to whatever profit-making activity the company has. And so shadow prices, the values in the y vector, indicate the increase in the objective value per unit increase in the corresponding right-hand side of a constraint. Okay. Um, if the constraint represents a limited resource, um, then the shadow price is sort of the maximum that you'd be willing to pay to acquire more of that resource. Okay. So let's look at Geppetto's problem. We've got three limited resources. We've got a limited amount of finishing labor, a limited amount of carpentry labor, and a limited amount of demand for soldiers. Okay. We can put this into a tableau, do our row operations, and we'll end up at a final tableau that looks like this. Let's go ahead and label this tableau here. So kind of labeling my column Z, X1, maybe I'll note here, X1 is a number of soldiers, and X2 was the number of trains that Geppetto is making in his toy shop. So X1, X2. Then we've got slack for finishing, slack for carpentry, and slack for demand, and our right-hand side. And then at this point, our rows, we can label them with the current basis. Z is always the basis for the objective row. This row here has a 1 and the standard basis vector with x1 for the first constraint row. So x1 and then x2 corresponds to this row. And then the slack for demand is the last basis variable. Okay, so we've got them labeled. Let's go ahead and read off the shadow prices. Now, the shadow prices are the values underneath the slack variables in the objective row. And so I'll call this one Y finishing because it's the value underneath slack for finishing. So there's essentially a shadow price for each of the slack variables or for each of the constraints. So Y finishing is 1, Y carpentry is 1, and Y demand is 0. So what do these shadow prices mean? Essentially, these shadow prices are telling us how much we're willing to pay for more finishing or carpentry. And so in this case, because both of these two are 1, we are willing to pay $1 for each additional unit of finishing or carpentry labor. So a dollar above and beyond what we're already paying. And so if you think back to maybe the scenario, and it's maybe been a while back that we put the full Geppetto's problem up, we baked in labor costs already into the profit. And so this is sort of maybe we're willing to pay a dollar more than what we're already paying for each additional unit of finishing or carpentry labor. Okay. Notice on the other hand, we're not willing to pay anything for more demand. Okay. We're not fulfilling our demand for soldiers. Right now, we're making 20 soldiers and 60 trains, and we've got 20 units of slack for the demand constraint. So that demand for soldiers constraint is not limiting our production of soldiers right now. So we wouldn't pay anything to get more demand for soldiers, right? We don't want to start some advertising campaign or anything like that to drum up more demand for soldiers. Okay. Now let's turn to this idea of how much the profit would change if we changed our right-hand side. So right now we have 100 hours of finishing available. What would happen if we were to up it to 120? Well, our objective, we can write Z as being equal to Y transpose times our original right-hand side, or times our right-hand side. It'll be a modified right-hand side once we change that to 120. And so this is going to be equal to our 110 is our Y transpose, reading off the 110 from here. Our right-hand side is, well, we're going to change what was 180/40, and we're going to change that to be 120, 60, and oh no, 120, 80, and 40. So these values, but I've just modified the amount of hours for finishing there. And so essentially I take this row times this column. So I get 1 times 120 plus 1 times 80 plus 0 times 40. And I get a value of 120 plus 80 is 200. Okay, so I increased my finishing hours by 20, and my new objective value would be 200, which compared to my previous objective value was 180, so it increased by 20. So the 20 additional units each got me 1 additional unit of profit for each of them, and so my new profit is 200. Okay. Would this be still be a feasible solution? So to do that, let's maybe kind of point out a couple of things here. So Z is going to be Y transpose B. This here, which are the values of the current basic variables, that's XB. And if we think back to our fundamental insight, that's equal to B inverse B. Okay, well, what's B inverse? Well, B inverse is right here, right underneath our slack variables. That gives us our B inverse matrix. And so if we want to change our right-hand side, and actually kind of looking back at our fundamental insight here, if we change the little b vector, the only place that shows up is here and here. So it'll change our current objective value and it'll change our current basic solution, but it won't change anything else in the interior of the tableau. It won't change anything in the objective row as far as changing whether or not our current solution is optimal, but it might change whether our current solution is feasible. And so let's go ahead and figure out what XB is, and that's going to be B inverse times B. The B inverse matrix, I'm going to read that off from right here. So it's 1, -1, 0, -1, 2, 0. and negative 1, 1, 1, multiplied by that same new vector of 120, 80, 40. And I'll get 1 times 120 minus 1 times 80 and 0 times 40. And that's going to give us 120 minus 80. Next row, I'll get negative 120, 2 times 80. So negative 120 plus 160. And then last row, I'll get negative 120 plus 80 plus 40. And so working those out, that will give us 40, 40, and 0. And those are our values for X1, X2, and slack for demand. Okay, because those are still our basic variables. Okay, so is it feasible? Well, I just need to check my basic solution and make sure that all the entries are greater than or equal to 0. In this case, they are. So the answer is yes, feasible, but barely. If we increase it anymore, actually this slack for demand actually then goes negative, because at this point, now we're right up at, we're fulfilling all 40 units of soldiers. So we're maxing out the demand for soldiers. And if we were to increase the supply of finishing hours, we'd run into that constraint. And now the demand for soldiers would be limiting us. Okay. So go ahead and try this next one. What if we changed, I think I meant to say this was carpentry hours. So try this next one. What if there were 100 carpentry hours available? What would be the profit, and would this still be a basic solution? So do the same computations. Now with a new B vector, maybe I'll call here. I'll call this B bar for new B vector. And in this case, it was 120, 80, 40. And now try out a different change where we're looking at 100 for finishing, but now do 100 for carpentry and still 40 for demand for soldiers. So pause the video, try that one out, and then I'll show you what we've got once you've given it a try. Okay, here's what you should have got. So if we bump up and get 20 more units of carpentry, then because carpentry has a shadow price of 1, those 20 units of increase in carpentry will lead to an increase of 20 in the objective. So also get 200 as our objective value here. And then our new basic solution will take B inverse times B using that same B inverse matrix. In this case, we'll multiply to get 0, 140. And so if we have more carpentry available, we'll actually stop making soldiers. We'll make 100 trains, and we'll have 40 for our slack for demand for soldiers because we're not making any soldiers anymore. So yeah, and if you had 20 extra dollars lying around to make the investment to increase the right-hand sides to obtain more finishing or carpentry labor, then you'd maybe have a choice of whether you wanted to increase the carpentry or increase the finishing, and which of these might be more preferable as a solution. So this one sort of you have balance between the two products. This one, maybe you save some setup costs, and now we're only making one product, and that's maybe a better strategy for your company. So Geppetto's got some choices. So this wraps up shadow prices. Shadow prices are a really helpful item to get once you're done solving. It's the values in the row, in the objective row beneath the slack variable, and it will tell us essentially the values that we put on each of the constraints. and the limited resources there, and maybe we might be willing to increase some of those resources. So that's it for this video.